Any of you guys watch Game of Thrones?
I read the
Yeah, it's just not a book. I like that kind of book. I just never got into that book series, so I haven't read any of the books. But now I'm kind of like, I always hate reading the book after I've seen the visualization.
They actually follow the it's okay. There's always the
I do this to myself.
Something else that's good is Netflix Daredevil. Yeah. All right, guys. So this is one of the ways to write cosine 2x, right? That's one of the ways. And there's another way to write it. This is the connection between a double angle and half of that angle, which is the angle. You guys with me so far? Do you see whatever the angle is? That one is double it, right? Yes. Right. This is x. This is 2x. So this is the connection between x and 2x, an angle and twice that thing. Okay. So far so good. So I can solve this for sine squared. All right. I didn't show it because it's easy to do. Now here's the part. So this right here is called it's very often called power reducing. The book calls it something sort of like that. Power reducing formulas. You see how it was squared, and on the other side it's no longer squared. So that's why it's called power reducing. To me, it's just the middleman. Who cares about this shit? What I want to get to is what a half angle formula would be. So all you do is, if I put right there, if I put like they have in the book, u over 2. What's got to be on this side?
1 minus cosine 2.
4.
Cosine x.
Whatever u is.
Yes. Okay, good. U. Because what does this do? Twice that. That's what this says it does, right? That's what it's going to do, because that's what it says it does. Right? Math is very straightforward. So what is it currently? U, half a u. So I'm going to double it so I get a whole u there. That's using the form of the identity. It says whatever the hell that is, I'm going to have a twice it there. So if I put half of something there, I'm going to have the whole thing there. Over 2. And the same thing over here. And then you just take square roots of both sides, and there's your half angle identities. So it should not be surprising that the half angle identity is the exact same formula, just rewritten as the double angle identity. Right? If I am twice as old as you, you are half as old as me. I said the same thing. Yay! So this is a double angle because it's explicitly written twice that. But what's x related to this? It's half of that. So I can just say that more explicitly, make it half the angle. You guys with me? This is more useful. Every angle that we know, twice that angle we also know. 45 degrees. We know everything about 45 degrees. So what's twice 45? We know that even better. Shit. Right? So what's more useful is half. I know 45, but what's half of that? 22 and I don't know shit about that. So this equation is actually more generally useful. Half angle, to be honest. This one comes up in identity work. It comes up in real life, and then you have to know the identity to rewrite it. This one is actually more computationally useful to figure out sine of some weird-ass angle like 22.5 degrees. All right, so enough of that. And you can apply the half angle over and over and over again to cut that angle in half and half and half again. And you can get a lot of angle exact representations of sines and cosines of angles that way. Okay, that's enough of that. Whew. Is that good? All right, good, because I have nothing else to add there. That was all I had. All right. So I want to get back into chapter 7. I'm going to sort of finish it out today. I'm going to at least show you what else I can throw at you in the little bit of time we got left here. Before I do that, here, Morty. Sorry, buddy. Almost at this time, right? I'll give you this. Even if you print out the whole thing, this has got some changes on the dates and stuff. So still on this.
same as on the back of our original worksheet?
No, this is okay.
Oh.
It's almost the same. So you can see my proposal here. I'm thinking between today and tomorrow we'll get into Section A1. And actually I kind of like that idea because Section A1 lays the groundwork for an entire different way to plot points. And that sounds exciting, I know. You guys are like, what? What's wrong with the freaking way we do it now? A lot is wrong with the way we do it now, believe it or not, in some situation. And then Section A2 is where we start to graph equations using that new coordinate system. So kind of like the idea that, guys, for this next test, we'll get used to the coordinates themselves, and then the next thing we do after that will be actually using the coordinate supply equations. They're called polar coordinates. And you get stuff like cardioid and lemniscates and all this. It's like that spirograph game. You ever had that? You remember the spirograph game? They have different gear sizes. That's too bad for you youngins. You don't know what you're missing, man. Beat the hell out of Xbox.
I have no idea.
Not really. You just didn't know.
That's a good guess. They were the kids playing Xbox.
8-1 homework will be due Thursday. Yeah. Cool. All right. So it's we sort of got this 7-4. We actually got a little bit.
I just have a question. So the
Finish
test
there.
is going to be from 6.5 to 8.1.
That's right. Exactly. Instead of all the way through the end of chapter 8 like it was supposed to be in the original one. Right? Yeah. All right. Lemniscate. Just to get us back in the groove here, if I said solve this monster.
So if you add the different sizes, you get kind of that stuff,
And how do you solve this?
then add 3 and square.
Add 3 in square root. Right. And when you square root, what would you put?
Square. Oh, sorry. So
Tangent theta, that entire expression is a variable itself.
so tan theta.
Tangent theta represents a number I don't know. So it acts just like x does. So you can factor it even. All right, so we'll see that in a minute. Add 3, take a square root. Hopefully square root of 3 looks familiar. If you're like me, I never memorized tangent's values. I never did. I just know that tangent goes like sine, because sine's on the top. So this is bigger. It could be root 3 or it could be root 3 over 3. So I know I'm at the place where it's bigger, and where is sine bigger? 60 degrees. Right? So I know this is going to be some kind of related to pi over 3. Are you guys with me so far? I mean, so this step is not a calculator step. It is you should know step. You should know what the base angles are. Now, tangent theta is plus or minus rad 3. So what quadrants will I be in? All 4. Oh, that's what you meant. But all 4. Right? Because it's plus or minus. It's positive here and here, and it's negative there and there, and it's all 4 of them. So remember, what's the very first step when you really start to figure out what theta is? Get all the answers that are from 0 up to
2 pi.
2 pi. Good. So I want to find where are the answers from 0 to 2 pi. Where are those? Pi over 3. Where else? 2 pi over 3.
3 pi over 3?
No, 3 pi over 3 would be that. It's a good guess. So I like that. 5 pi over 3. Where's 5 pi over 3? Careful. You went and skipped one on me. 4 pi over 3. There you go. Alright. The 3 pi over 3 is just pi. That's not part of this, right? Alright, I like it. Are these evenly spaced?
Yes.
Based off of what just happened? Think. How far apart are these?
90.
They're not 90. Don't guess just because of the way I drew it. Don't guess anything based on the way that I drew it. Holy shit. They are pi over 3 apart. How do I know? 2 pi over 3 minus pi over 3 is pi over 3. What's 4 pi over 3 minus 2 pi over 3? Because I had to skip that one, didn't I? And this one didn't have anything to do with the problem, right? So these are 2 pi over 3 apart. These are pi over 3 apart. Why am I talking about that? And you're like, that's exactly what I was just thinking. Because I can go from pi over 3 to 4 pi over 3 easily, right? Do you guys understand what I'm doing now? I've got my 4 base answers, but do I need 4 lines here? No. But can I do it in 1 line?
No.
No, because they're not equally spaced between each other, right?
Yeah.
So my 2 base ones I'm going to use are pi over 3 and 2 pi over 3. Because from pi over 3, how far do I go to get over to this one? 3 pi over 3, which is pi. Cool. And what's the period of tangent? Nice. All right, so theta is pi over 3. Theta is 2 pi over 3. I know I don't need 4 lines because from 2 of these I can get another 2 of them. But I can't do it in 1 line because they're not evenly spaced. The one we did last time were all 90-degree angles. I made it specifically that way. They were 45 degrees here. So then I did it in 1 line. Remember that? We did that last time. So a lot happened this weekend. For me, I don't know about for you, but so I can almost remember that. And then I can just off of here, I want to add pi. Okay, cool. So if you weren't here last time, how do I get from pi over 3 to 4 pi over 3? I add pi, right? And then if I add pi again, I don't get here, I get to the same place. I get to 7 pi over 3. So really, to almost any trig equation, if there's an answer, there's more than likely an infinite number of answers because it's periodic. It keeps having the same outputs over and over and over and over again. I like it. So almost every time you solve one of these things, it's going to look something like this. That represents all the answers. This represents all the answers that are positive, and this one represents all the answers that's awesomeness, right? Awesome sauce.
Oh, because they're both in quadrants that would be negative.
Kick-ass, they're both positives, so tangents positive. They're both negatives, x and y, so the tangents ratio is still positive. I love it. Kick-ass. Awesome. All right. So here's a little twist. Right off of this, let's look at this here. Let's see if you guys are, well, let's see, let's try this one here. There was something that came up last time that's actually a very, very important idea. If I'm trying to prove identities or solve equations and the arguments aren't the same, that's kind of the first thing I attack. It's sort of like somebody giving you a problem in a science class and one part's in feet and the other part's in meters. You're like, yes, let's convert my freaking units. I got to make everything agree, right? So these guys are talking about entirely different angles. Shit. How can I make one of them talk about the same angle as the other one? I cannot divide by 2 because nowhere up there is it saying 2 times something. It's a sine of twice an angle, right? What is sine 2x? That is an identity that we built off of the double. Well, it's the double angle coming off the sine a plus b. That beautiful one. Hopefully, you guys got my corrected. I love that I did that. Can you get an email from me with the corrected thing? Yeah, it was awesome. And then what the hell do I do here? Shit. Factor sine x out. Kick ass. So I get sine x times 1 plus cosine 2 cosine x. And then, of course, we know how to solve an equation from there. We factored it so that we could do what? What's the next step here? We can always cry a little bit. In fact, if you don't, it worries me. What's the next step here? You set each one. So here, you set each one of them equal to 0. Trig functions are variables. They're things I don't know. They act just like x or y or whatever the hell you want to call them. So I'm going to set this factor equal to 0, or 1 plus 2 cosine x equals 0. If either one of these are true, then this equation is true, correct? And that's the only way those are the only two ways that equation could be true. If neither of them is 0, there's no way that equation is true. Are you guys with me? Can you multiply some non-zero number times another non-zero number and get 0? If you can, show me, please. Right? You have reached infinity, nirvana. You must show me. So when is sine x equal to 0? I love it. Okay. So it's 0 and what else? So if I draw a little picture for myself, it makes it easier. 0 and pi. And do I need 2 lines to answer that then? Because they're equally spaced, right? It's pi to here and then it's pi back. So I can say it's 0 plus pi k. So I can really just say it's pi k. Pi k. No, pi k. And then, maybe that commercial is too. If I solve this for cosine x, I get what? Negative 1/2. And what is cosine negative 1/2? What quadrants are we talking about?
2 and 3.
That's awesome. I love it.
2 and 3.
Just like,
2 and 4.
can't say I'm wrong.
2 and 3.
Yeah, be careful. 2 and 3, yeah, I think that's what I was for. Yeah. So 2 and 3, my cosine's going to be negative. And where's it going to be 1/2? What angles?
6 pi over 6. 3.
Yeah, so
pi over 3.
pi over 3. Further away from the x-axis is when cosine's smaller, right? Because cosine likes x. Further away from the x-axis is smaller. So this is going to be some reference angle of pi over 3. So what angle is this going to be? 2 pi over 3. And then this is probably going to be 4 pi over 3. Are they equally spaced? Do you see what I mean by that? To get from one to the other one is 2 pi over 3. Now how do you get all the way back around? Do you go the same amount? No, so you can't do it on a single line. You guys start to see how to look at that? I mean, the last hard step in the problem is, how the hell do I write the answer? You can't do it in one line. You got to use 2. So this will be pi over 3 plus 2 pi k. I love it. Because if I go all the way around and come back, I get another answer. Or 4 pi over 3 plus 2 pi k again.
Wouldn't the complement be 2 pi over 3?
Oh, I'm sorry. Yeah, 2 pi over 3. Thank you. So I can get from one to the other one, but I can't get back by the same step size. I can't. That's what tells me I can't do it in one go. Why can't I do this one in one go? From one to the other one is pi, and then how do I get back to the first one? Pi. Okay, so they're equally spaced. That's why I can do it in one line. Yes. I guess that's enough. We'll finish up chapter 7 next time. I'm all bummed out.
Once you find one of them equals 0, does the rest matter?
Well, you've got to allow, if this isn't 0, then when is this one 0? And that'll be all your answers. Right? Cool.